Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It is my pleasure to welcome Matthew Taylor to MSR today. Matthew has been doing great work on reinforcement learning, multi-agent systems, and robotics, and I've been following his work personally for a while. So I'm looking forward to hearing what he has to say. He is currently an assistant professor in Washington State University and has great master student, grad students that he is collaborating with. So I think you're going to be talking about that work today. So, Matthew.
Thanks. It's exciting to be here. So just a little bit of context. Li Hong and I work on some similar projects. We haven't worked together, but I am working with his former PhD advisor. John and I have been working on an autonomous wheelchair project where he's been helping to supervise a bunch of undergrads who have been doing some cool work as part of their senior capstone courses. And Ejay and I are hoping to work together. We actually just submitted a tutorial proposal for AAAI. So there's a chance we'll be talking about interactive machine learning, which happens to be the talk of what I'm talking about today. So like I said before we started, as a professor, I love hearing myself talk, but it's really more interesting if you all interrupt me. So do interrupt with questions, comments, anything. I, on purpose, have more material than we can fit in the time. So there is, if I only get through half of this, that is totally fine with me. What I'm going to be talking about today is mostly reinforcement learning. And it's really a pretty exciting time for reinforcement learning agents, in part because of the empirical successes by DeepMind with AlphaGo. There are more startups now that are actually taking reinforcement learning and trying to put it in the real world. So for a long time, I felt like reinforcement learning is supervised learning's little brother. We're not as important, we're not as useful, we're not as flashy, and finally, we're getting the recognition that we deserve. Well, more people are paying attention anyway. So just so that we're all on the same page, when I say reinforcement learning, I mean that we have some agent that's interacting with the environment. So this environment could be a Go board, it could be a car interacting with the world around it. It could be an agent in a video game. And that agent is going to take actions that somehow affect the world around it. And based on those actions, the state of the agent is going to change. And the agent will receive some reward. And that reward could be time delayed. It could be stochastic. So we describe the world in terms of an MDP. There are states, actions. There are transitions. Given a state-action pair, where do you end up? There are rewards, there's a discount factor, but our goal is to learn some policy, saying that when I'm in a state, what should I do? What action should I take to try to maximize my reward? One way of learning that policy is to estimate a Q-value function. So saying how good is a particular action for this state. So given my state, I could look around and say, okay, these are all the actions I could take. I'll pick the one that will give me the expected best long-term reward. So this is awesome. Reinforcement learning has had a number of recent successes, like Ejay and I were saying before at DeepMind. If you have a simulator, like an Atari emulator, and your agent can play with that simulator for months at a time, that's great. Unfortunately, there's a lot of situations where you're not able to interact for months at a time, because there's some cost to that data. Or it turns out you're using a robot and you have wear and tear on the joints and you have some poor undergrad that has to swap out the battery every 20 minutes. So I've been thinking about how do we inject human knowledge? So one of the ways you could do that is try to give the agent some extra data. So you might try to show the agent a success condition, try to show it what it should do. And maybe you want to have some variance in what you're showing. And that could give the agent some bias. But then at some point, you might actually just have to teleoperate that agent and tell it exactly what you want it to do. And that's what I'm going to be talking about today. So at a high level, my research looks at how can an agent learn on its own. That's pretty well well, I shouldn't say understood. There's a lot of people looking at how an agent can learn faster on its own. I've been more interested in these interactions. So thinking about, if I have one agent that knows something, how could it teach another agent to do that? So if I have a robot at home that's learned how to perform tasks in my house, and I get a new robot by a different manufacturer, how can I speed up learning? And what I'm going to be talking about in a minute or two is how, if a human knows how to do something, how can the human provide some demonstrations to help the agent learn faster? We're also looking a little bit at this third direction. If the agent knows how to do something, like play Pac-Man or solve some sort of task, how can the agent teach the human to learn faster? So I'm really interested in all these different teaching directions. What I'm going to start with is talking about human demonstrations. So the simplest way to think of this is, if I have an agent that wants to learn to play a video game, I could watch a person playing that video game, and that should help me. Depending on time, I'll also talk about learning from human feedback. If instead of having an environmental reward, so the score in a video game, you could also think of a human providing feedback like you would a dog. Good agent, bad agent. With the learning from demonstration, I'm really interested in techniques that work with normal humans. Because a lot of our research is computer geeks teaching robots or teaching agents how to do things. And the problem is, we already know how the machine learning algorithms work. So ideally, however we're doing this teaching, it would work for non-expert humans, people who don't understand AI. And whatever techniques we're using, hopefully, when the human shows these demonstrations, the agent will be able to learn faster or learn better. But because humans are typically suboptimal, we want to make sure the agent can outperform the human. So what I want to do is go through, this is a little bit of a tutorial, because this area is not as well known as I think it should be. So what I'm going to do is go through a few different methods that people are using, and then coincidentally show some of my own work that just happens to improve on the stuff I'm going to talk about. So the first method I'll mention, so we talked about reinforcement learning with just autonomous interaction. I mentioned that briefly. Another competing paradigm is learning from demonstration, similar to programming by demonstration, where it really came out of the robotics community, where you have a human teacher who provides some demonstrations, and then you've got some kind of learning algorithm that will execute what basically try to mimic the human. So if you have a complex robot, many degrees of freedom, learning may be too hard autonomously, so you just want the robot to be able to mimic the human. Now this is a great way to get some baseline behavior, but I argue that we really want to then improve on that, because however we demonstrate a behavior to a robot, it's probably going to be suboptimal. And we'd like to use our machine learning techniques to actually get near optimal performance. One of the ways we can build on learning from demonstration is we can use it to seed a policy of a reinforcement learning agent. So this is some work we did back in 2011 with Sonia Chernova, who's an expert in learning from demonstration, and a student, Benir Sway. The goal of this work was to kind of combine these two paradigms. So we first have a human that provides some demonstrations. So we can have a human play a game. And then we take, as the human is playing that game, we record state action pairs. So we say, when the human's agent was in this state, what action did they take? And we can take all these state action pairs, and that's just a data set. So this is similar to normal learning from demonstration in that it's just a data set. We could try to mimic what the human was doing and then replicate the human. We wanted to take what the human was doing, take all that data, and summarize it in some kind of a policy. A way of then a classifier that could say, given this state that the agent is in, what action do I think the human would have taken? We chose JRIP mostly for the reason that it creates these human-readable rules. So we're able to have the human demonstrate a policy and then summarize it in a few lines, in this case, a few lines of code, a few if-then-else statements. Then, if we just followed this decision list, we would try to replicate the human's behavior. You wouldn't be able to replicate it perfectly because the human only demonstrates for a certain amount of time. The human can't exhaustively demonstrate, so there'll be some places where our classifier is wrong. So what we want to do is, in normal reinforcement learning, with some probability, you explore, and with some probability, you exploit. So if you're learning Q values, that's your estimate of what is best. Most of the time, you execute the action you think is best, and sometimes you explore, so that over time you improve. In this setup, what we want to do is we still have explore and exploit, but now we've got this other choice, which is take the action suggested by our classifier. So if we only execute the decision list, we're saying just try to do what we thought the human was doing. And initially, we will just execute this decision list. But then over time, we will take some random actions, explore, and we will exploit. We'll slowly use our own knowledge. So this means that places where the human's decisions were suboptimal, we can try to improve on that. Yeah?
So when you're doing exploration, exploitation, and observing new things, is the goal updating the model of upstairs, the above one, which is the if-else statements, or completely move the formalization to a Q-learning kind of framework and now try to accumulate Q values instead?
Right. So you could do it either way. We focused on just learning the Q values. So this information we learned from the human stays fixed. We could also think, and that's one thing, if we wanted to make it explainable, if we wanted our policy to be explainable to the human, we could try, instead of learning Q values, to just update this list. That would be particularly interesting if we wanted to say, hey, human, when you do this thing, that's actually not as good as if you did that. You know, so if a person was playing a video game, to help them improve their video game playing. Here's a typical learning curve in reinforcement learning. On the x-axis, we have data or training time. In this case, we're looking at simulator hours. And on the y-axis, we have performance. So what we see in the red line, here's what you get when you use reinforcement learning without any prior knowledge. And with the purple gray triangle line is what you get when you use this learning from demonstration information. So there's a few interesting things here. First, when we start off, we're actually doing slightly worse. So this means if we just try to mimic the human, it's actually not that great. Mostly because we only ask the human for 3 minutes of training data. So what we were interested in here is saying, if I've got this task which is going to take hours, how can I get just a tiny bit of information from a human and leverage that? So the information we get isn't that great if we just try to follow the human because we haven't gotten enough data. But it is enough to help bias us to learn faster, as it turns out. Yeah, Leon.
What does the no prior have at the beginning? What information does it have?
Nothing. Just zeros in the Q table. So this is a way of coming up with some way of biasing the agent through a demonstration.
So somehow it seems that the initial bias of hat is makes the point a little bit lower than having no prior at all.
Yes, and I think that was something that only happened in this learning curve. I think in some of the other learning curves in the paper it was the other way around, but it was always fairly similar.
Maybe not similar.
Yeah, and what you would really like to see if I could have everything would be for the agent to start learning with a really high performance, have a high jump start. But in order to do that, you would need much more data. So if we collected 15 minutes of human data, we might have been able to do that. That wasn't really the focus of this paper. Yeah?
So, but is this within the tabular case or with function approximation?
This is with function approximation.
What was your function approximation?
We were using a CMAC here. This is the keep away domain. Yeah?
Looks like the state and the rules from the human were discrete, not approximate. How do those compare to the function approximation?
So let's see. So how did they compare to the function?
Is that the state I'm seeing, the K1 comma T1?
So this is one of the features that describes the state. So you're right, I didn't go into any detail. This was a simulated soccer game. So one of the ways of describing state would be, what's the distance from one player to another? Or what's a passing angle?
Those are given as features, okay.
Yeah.
And that can deal with that directly, and then they feed into the function approximation?
Yep.
Okay.
Exactly. So this was the method of combining learning from demonstration with reinforcement learning, trying to inject some knowledge from a person where the person provides minimal input. One of the classic ways of improving reinforcement learning is reward shaping by Andrew Ng and others from the late 90s. And in reinforcement learning, you have a reward function, which is often sparse. So you could think of, you're playing a game and maybe you get +1 every time you cross the finish line. Or you get a +1 every time you get a gold coin, but there aren't many gold coins. The idea behind reward shaping is, well, if we had some extra information, we could inject that information and help the agent learn faster. So think about it this way. If you're playing a Mario game and you're trying to get Mario to the end of the level, maybe your shaping function gives you more and more reward as you get closer to the end line. And if you go away from the end line, you go away from the goal line, you get less shaping reward. What was interesting about this method is they used potential-based rewards. So I as a person could say, oh, give extra reward when you move to the right. But the problem is, if I gave that policy, and that's not a potential-based reward. So what could happen is the agent could move to the right, get a +1, then move to the left. Move to the right, get a +1, then move to the left. Whereas if it's a potential-based function, that means if you move to the right and get a +1, if you move to the left, you get a -1. So by figuring out we want to add some extra information to the agent through humans being smart, we can figure out, well, if we add rewards using this kind of formulation, then we won't change the optimal policy. So this is a really cool idea. If you as the designer could come up with a good potential-based reward, then your agent can learn faster and you won't change the optimal policy. Of course, the question is, where does this reward come from? Now, if you have a non-expert human, it could be pretty hard for them to make a potential-based reward function. The similarity-based shaping is trying to use this shaping idea and improve on it. This was something we presented at ICHCAI a little over a year ago. The goal of this is we looked at a human demonstrating. So this is the same setup as before. A human demonstrates, but rather than trying to learn something from the human's data and summarize a policy, we want to create a reward function based on the demonstrations. So one way to think about it is, I want to create a potential-based shaping function using these demonstrations. And you can kind of think of this as, I'm going to throw Gaussians in the state action space so that when the agent takes actions that are similar to what the demonstrated actions were, it gets rewarded. And if we do it right, if it's potential-based, we won't change the optimal policy. So rather than asking the human to provide a reward, let's take their demonstration and try to come up with a reward. And one of the drawbacks, which I'll come back to later, is this is all local. So this means, if you think I've got some state space and maybe the human's demonstrating and adding these Gaussians, and that's great when you're down here, but when you're up in this area of state space that you have no demonstrated data, you're out of luck. It's not going to help you at all. I think I'm going to skip these details. So let me show you another graph. So this is the Mario domain. Hopefully everyone's played Mario. It's in our case, we have a 27-dimensional state space. So we've got these 27 features that describe the state of the world. Things like, how close is an enemy to me? Is there a pit right next to me? Is there a coin above me? Things like that. So in red, we have learning without any prior. In yellow here, we have the learning from demonstration. So this is if I took the data that the person demonstrated and tried to replicate that policy. So here we see, similar to before, we get a little better than random, but not great, because we don't have a whole lot of data. And there's no improvement over time, because we're just trying to replicate what the human was doing. If I do my trick with HAT, so I record this data and learn a decision list and then try to use that decision list to learn faster, in this particular domain, I get a little bit of benefit, but then it goes away quickly. So we add our new method as of 2015, where we've got this similarity-based shaping. And what happens is now we place these Gaussians, this potential-based shaping function based on the demonstration, and we see we learn much faster. So it seems like learning a shaping reward from a demonstration, rather than trying to directly leverage the policy, gives us some benefit. Yeah?
So when the episode is 0, so the agent hasn't explored anything yet, why is HAT doing so much better than LFD?
Yes. Okay. So HAT at the beginning, at episode 0, is going to be almost entirely exploiting the human's data.
And LFD is exploiting human data as
Yeah.
well, right?
Yes.
But it seems to be doing that much better than LFD. So I feel like HAT and LFD should be doing the same thing.
Yeah. Actually, now that you mention it, that's a good point. I don't have a good explanation for why this starts off so much higher. My guess is that there was some really minor error that the LFD classifier picked up, and then somehow RL managed to compensate for it quickly, but that is me talking out of the air.
So you could actually imagine a green straight line
Yes.
that goes from that square all the way.
Yeah, and that might be a better comparison than this. Yeah. So that's a good point that I need to ask Ben about. Yeah.
So the shaping is based on the exact same user demonstration data.
Mhm.
It's just interpreted a different way.
That's correct. Yeah, so there's something about this shaping reward where we're guaranteed not to change the optimal policy, which is somehow better than trying to leverage this policy directly. Yeah.
How is this related to if I were to do, like from the human demonstration, inverse reinforcement learning, come up with a noisy, very noisy reward function, and then inject that reward function as the shaping reward? Or is that precisely what this is? Or
So here we're trying to build a reward function based on that demonstration. What you're hinting at is, what if we looked at that demonstration and tried to figure out what reward the human was trying to optimize?
right.
And that's inverse reinforcement learning,
Right.
and that's going to come up in 3 slides.
But what I'm saying is that, what if you took that reward function from that estimate of the human's intrinsic reward function and used that as the shaping?
It works better.
Okay.
Yeah, so this insight that took us like a year to come up with took you 30 seconds. That's awesome. Okay. Another method I'm going to mention, this is by Anne Noé's group from AAAI a few years ago, where here they came up with this dynamic shaping method. The idea is, we know potential functions are great. Potential reward functions let you learn without changing the optimal policy. They came up with a method where you can take any reward function and do this extra Q-value function trick to turn it into a potential-based reward function. Unfortunately, there's not a quick way to explain this. So at this point, I'm going to wave my hands and say, if you're interested in this trick, I'd be happy to talk about it offline. The way to think about it is, I'm using an extra Q-value function so that I learn that I've got a function I actually care about, and then I can learn to output a potential-based function. So this was some really cool work, and I say it's cool because we were able to leverage it. I'll show you that in a sec. So this is a good general tool in reinforcement learning. If you have some kind of knowledge, but it happens to not be potential-based, this is a tool you can basically use out of the box to change your reward function into a potential-based reward function. The last thing I'm going to mention is inverse reinforcement learning. And in IRL, you typically have a model of the world, but you don't have the reward function. So you can figure out, okay, I know how I could act in the world, but I don't really know what I'm doing. Or I don't really know what I should be doing or what I want to do. So if I watch a human, I can figure out what if, of the infinite number of reward functions, what is the most likely reward function that the human would be optimizing if what they were doing was optimal? So there are a few methods that are also model-free, which is what we're going to leverage, where the idea is you can try to look at the human demonstrations and figure out what is the reward that I think the human is trying to maximize. So what do we have? We've got our two base methods in the upper left, learning with reinforcement learning with no prior, which is really successful but can be slow. Learning from demonstration, which does not improve on generally does not improve on the human. Then we've got a couple of methods that try to take human demonstration. One of them tries to directly use the policy from the human. One of them tries to make a shaping function based on it. And there are these other tools that we have. We really want potential-based rewards. We can use this trick, this dynamic shaping trick, to make potential-based rewards. And there's this inverse reinforcement learning thing where we can try to figure out what the human is actually trying to maximize. So this is a very long introduction to what I actually wanted to talk about, but hopefully this is interesting for those of you who haven't been really familiar with how can humans inject knowledge into reinforcement learning. Hopefully this will provide you at least some ideas and references. So we're building up this body of work over a few years and finally getting to what we presented in Singapore this last spring, where we're actually leveraging inverse reinforcement learning. So this is combining a few of the things that I've shown you so far, and you can probably guess by the way I'm building up, this works better than all the things I've shown you before, otherwise I wouldn't have shown them. So what do? We collect these demonstrations, and we're going to look at these demonstrations and use inverse reinforcement learning to figure out what the human's reward was. So in the first domain I'm going to show you, we had a maze, and you get a +1 for getting to the exit of the maze. Very sparse reward function, takes you a long time to learn. You can pretty easily learn a shaping reward that gives you some indication, oh, it's better to go towards the goal than away from it. This method, static IRL shaping, is going to use a potential-based reward over states. So what we're going to do is we look at our demonstration and try to figure out which states are better than others. States towards the goal, closer to the goal, are better than states further from the goal. It's not actually telling us about the actions, how to get there, but this type of reward should help us learn. Here, we learn the demonstration, we record the demonstration, learn this function, and it doesn't change. Static IRL shaping, the other method that we presented at AMOS was dynamic IRL shaping. So it starts off the same, we collect some demonstrations, we learn a reward function using states, and here the difference is we'll also use the actions. So instead of a shaping function just over states, we want to learn a shaping function over state action pairs. So rather than saying, okay, you move from a state closer to the goal, that's good, that was our previous one. Now we want to say, oh, you move from a state closer to the goal, and I see you took the right action. So it's not just, and this is important if there's a stochasticity in the environment. So if you take a stupid action, but you're lucky and slip and stumble towards the goal, you don't necessarily want to reward that. Because we want to use shaping over state action pairs, this is where this trick comes in. It's no longer a potential-based function, so we need to use this trick from Anne Noé's group so that we can transform it into a potential-based function. The key difference here is that the first one is shaping over states. This second one, this dynamic shaping, is over state action pairs. That's the main difference. And it's going to turn out that sometimes this method is better than the other one. But we're using the same data from the human. It's roughly the same amount of computation.
Is this the guarantee that this kind of shaping doesn't change the optimal policy?
Yeah, because it's still completely potential based. Yeah, so if our, go ahead.
It depends on the actions. It's potential, but somehow this can still cancel out.
Yes.
Okay.
So if the demonstration is good, this should help us learn faster. If the demonstration is bad, eventually the agent will still learn the right thing to do, but it would take longer. So that's kind of the worst case. So the first domain I want to talk about is this maze. We define our world in terms of two continuous states variables. We got a fixed start state. This is our toy domain where we can run experiments really quickly. There is a -1 on every time step. So this encourages you to get to the goal quickly. There is a penalty for hitting walls, and there is a reward for reaching the goal. So you start around here, and you're going to want to get to the goal state quickly. Our demonstrations were, on average, 27% longer than optimal. So what we did is we took a bunch of demonstrations that get to the goal, but they're not taking the optimal path. They're wandering their way towards the goal. So this is the kind of information that should help us learn faster, but we should be able to outperform it. We should be able to learn that optimal policy. And this is, in fact, what we see. So blue, I have the human's performance. If I learn using normal reinforcement learning, I start down here and improve over time. If I try to mimic the human's policy, I start off really high, but then I start exploring. And as I start exploring, I get very confused. And that's one of the drawbacks of trying to mimic a policy. We mentioned the static-based shaping, so I try to place my Gaussians and make a reward function. And we see a similar behavior. We start off high, and it gets worse because I start doing this exploration, and this reward function may not be as useful as I'd like it to be. So our two methods, static IRL shaping and dynamic IRL shaping, both do better. So in BEST, for some reason, I can't remember, I think we had a hand-wavy explanation why we do so poorly on the first data point. But very quickly, this using the inverse reinforcement learning, by using the human's reward, we are quickly able to outperform all the other methods. And the dynamic IRL shaping outperforms all the other things except the static IRL shaping. So we can learn quickly. And then if we can zoom in, we actually see that, okay, this is the human's reward, and indeed all of these policies, all of these algorithms do end up outperforming the human. So we are able to improve on the human's performance.
I have a question. In this experiment, can you explain once more what the state actions are?
Yeah. So the state is your XY coordinate, which is continuous. And the actions, I believe you have 4 actions, north, south, east, and west. And you've got some kind of probability distribution over how far it brings you. And I think there is some slippage. So that can make you go a little bit off from the way you're trying to go.
And then there are the obstacles in the world. Mm-hmm. That's also part of the state.
Yes. You can't see them until you run into them. And you get that -10. Ow, I shouldn't do that.
When does a demonstration, what does it mean exactly in this experiment?
Yeah, so what a human does is he's got his simulated maze agent and he's pressing the buttons on the keyboard trying to get it towards the goal.
But they're not able to see the map, the whole map.
Actually, the human can. So the human has this extra information that an agent wouldn't have.
They would only do one demonstration in this case, right? Or would they do more than one?
I think we had 10 demonstrations. In this case, it was the same human, the first author. A more interesting question would be how well can people non-expert people demonstrate. But for the purposes of this study, we just wanted to, it was more of a proof of concept. And something like a maze domain, most people can figure that out pretty quick. In the next domain, I'll show you different demonstrators will make even more difference.
The human's just not going around the corners as fast or something.
Yeah. Yeah, so the human is not taking the minimum distance path.
Do you have a plot where you have where you, let's say I run shortest path, and so I have let's say the computational optimal, and it would be interesting to see if all the policies can reach the computational optimal.
Yeah. So I would assume that the optimal is right around here, because we're using in this case we're using Sarsa. We have epsilon greedy action selection, and we're not decaying that exploration. So we don't. This is just showing the online performance. We don't have a separate testing phase where we say, okay, do the best you can. Even at the very end, the agent is still trying to tweak and find. So the absolute best is probably a little bit better. And with these methods, if we say, okay, stop exploring and just try to do the best you can, they should reach that, or at least get really close in a simple domain like this.
In this domain, you have the advantage that you can run the optimal. Right?
Exactly.
In many.
Whereas in the next one, in Mario, we have no idea what is optimal.
Exactly. Correct.
Yeah, so that would actually be a good double check to make sure that these are getting the near optimal.
Because it seems like the human's going to be sort of fixed time where the algorithm should speed up. Even though it's making more mistakes at the beginning, you can still probably outperform the human. There's some crossover point.
Yeah, so here it's a little weird, you're right, because a human demonstrating a maze, it's really easy, but it might take 30 seconds to demonstrate, whereas a reinforcement learning agent learning on this domain is super fast. So trying to compare the time the human spent versus the time the agent spent learning is less interesting than saying, if we only have a little bit of human demonstration, how can we leverage it? But you're right, in other domains where the learning, so like in the previous keep-away domain where learning takes hours, then it makes more sense to look at the time difference between the human and the agent. I'm not sure if I answered your question or just dodged it.
It'd be interesting to see at the very beginning, even though it's really performing poorly, should do it fairly quickly, even though it's going off and doing all sorts of crazy tracks, doing exploration.
Yeah.
So the action space between that the human used and the agent used is similar. Is exactly the same, right? But it would be interesting to see what happens when we change the action space. For example, augment the action space, right? Can the agent still recover? So maybe there's a new action which says jump, right? Will the agent be able to use those actions effectively even though the reward was initialized by IRL?
Yeah, that's a great question. Because I've never run that experiment, I'm going to say, yes, of course. Of course our method works there. So we've also looked at doing this, thinking about it as a transfer learning problem. So if I demonstrate in an easy task that the human can handle, can I speed up learning in a more difficult task? And the answer is yes. You could also think, like if I'm doing StarCraft, there are lots of micro options. So really good people playing StarCraft can click really fast. So in some sense, you could think of that as like a different set of actions. So So you could have a normal human demonstrate how to play a game and then have the agent, which a computer can click super fast, or is able to take some tricky action sequence that a human could never do, and essentially treat that as an extra action. And because we're adding the shaping reward and forcing the agent to still explore its full action space, if there are places where, for instance, the jump action was useful, if the human never demonstrated it because they never thought of it or they didn't have that option, the agent should still learn to exploit that new action.
The actual question that I wanted to go towards now comes into play, which is, so we did some experiments where we looked at augmenting the action space. So suppose a person knows Windows 7 and was making the transition to Windows 8, right? A completely different interface, right? Can you make that transition more efficient by having some sort of an intermediate interface which allows the agent to transfer to the new interface, although we know that maybe at equilibrium, once the agent learns how to use this new sort of action space very effectively, it will be much more optimal, but still, in order to just guide it, maybe there's a whole spectrum of action spaces it has to go through, and that brings to the question of, is there some sort of a curriculum learning sort of that could be created here over action spaces?
Are you on my schedule? Are we meeting later? Because Ajay and I were actually talking before this about my work in curriculum learning and what we want to do is say, so in your case, if you have two, how do you fill in the middle? We're thinking, if this is the thing I want to learn, how can I figure out the sequence of intermediate steps? And we've shown that a machine learning expert can pick those steps, and learning the entire curriculum is faster than directly learning on the final task. But what if you don't have that human in the loop? Can a machine pick that curriculum, or could a non-expert human pick that curriculum? And those are really important open questions.
I have another question.
Yeah?
So the human is definitely suboptimal in this game. But one question is, why is it suboptimal? Because I may claim that human could actually, in this domain, see and identify an optimal solution, but maybe the way you have to drive the agent over the maze, like the kind of particular input mechanism that you have, is making it suboptimal. So it's not like humans cannot identify an optimal solution, it's very hard to implement that optimal solution for a human. So if that is the case, you can imagine actually having different input mechanisms for the human to enter a better demonstration into this, rather than exactly simulating it with the same input mechanism of the agent. Anyway, so I think there may be some ways of being creative about how you should elicit that optimal policy from the human, rather than asking the human to do exactly what the...
But I want the human to be suboptimal so that I can beat him. But no, that's a very HCI sounding question, and that's kind of similar in spirit to what Bill Smart is thinking about with if you have a wheelchair user and you have someone who's directing that wheelchair and is directing it because they can't control their interface perfectly because of muscular problems or something else. How can you smooth that over, or how can you figure out what the person is trying to demonstrate rather than what they're actually demonstrating?
So I was thinking something similar, for example, instead of saying, okay, try this, you could actually say, okay, I'm going to show you a few paths, and I'm going to ask you to give me which path do you think is better.
Mm-hmm.
And I may be able to ask these kind of questions 100 times during one single demonstration of the human. And that could maybe lead to, if I find a better way of incorporating that kind of information into my learning, maybe that's more valuable information than seeing one demonstration of the human.
Yes. So, and there was a paper at AAAI last year, and there was one other, I want to say it was at ICHCAI, I think it was at ICHCAI, where they were doing this kind of learning from humans, but rather than asking for a demonstration, they would say, here's a bunch of trajectories, rank them. And then as the agents learned, you could think of getting more trajectories. And I think it's an interesting question. If you ask a human, so let's say, let me skip to Mario. If you ask them, okay, I'm going to show you 3 Mario games, tell me which is the best, versus, here, play Mario for me. I bet they would do better ranking those 3 domains, but they would probably enjoy playing it more. So where you would get better data versus where you might get more data because they're having fun. But you're absolutely right that there's all kinds of modalities that I'm ignoring. I'm just focusing on demonstration, and really would want to think about all the different ways we could solicit these kind of biases from humans.
So most of the stuff you've shown so far is about preliminary learning from the human, and then the agent just kind of goes off and does its own thing. Is there much work in the, I teach it a little bit, and then I come back later, and it's making suggestions, and I may or may not like those suggestions. If it tells me to do some crazy jump, and I think that that's a suboptimal jump because I'm a human, and I don't do it, and it turns out that that would have been better, or is there much work in that kind of general space?
Not as much as there could be. And that's, so, and I was, again, before this talk, I was telling Ej, one of the next directions I really want to go is, I've got a human that's advising the agent, and the agent goes off and does its thing. What I would really like is more of that back and forth. So the agent checks in after a while and says, hey, how am I doing? Or maybe the agent checks in and says, I've got this state, and every time I get here, I can't figure out what the heck to do. And maybe the human can say, well, no, you need to do this. Or the human could say, yeah, that's because you're going to die no matter what you do. Don't go to that state. So right now, our research doesn't do that two-way communication. A few people are looking at that, but it's not as popular as it could be, in part because of the timing issues. So how do I say, okay, I've got my agent that's maybe playing 10 of these games a second. How does it say, okay, I'm going to stop, ask the human, hopefully the human's paying attention, hopefully the human gives me a good answer, and then maybe that takes 30 seconds. So how do I trade off getting those 300 more autonomous trainings versus one answer from the human?
Would you expect the same sort of sharp increases in the optimal behavior that you see at the initial?
So if the agent chooses a good question, I think you could get large jumps in the learning curve. I think there's a lot of potential there.
And what about the sort of interruptive learning? You know, the sort of move over, I'm going to do this, and like it's unsolicited.
Yeah.
The human still thinks they're better.
That's harder.
Okay.
But yeah, because I'm saying it's just the one-time dumping of knowledge into the agent. You could think of the agent interrupting or the human interrupting. There was a question in the back, I think?
Yeah, I'm just curious. So we're learning these potential state values, kind of, right? But don't those change over time, and how's that?
So we're learning this potential reward based on the human's demonstration, and then learning, I guess I should go this way, we've got that as our bias, and then we're learning the actual Q values on top of that. So the potential reward is not going to change at all. We're just learning for places where it's wrong, we're learning to compensate for it. Okay.
So I have a question. So because you're using multiple demonstrations, human demonstrations for learning, have you noticed whether or not it attains an optimal based on the quality of the demonstration? So with StarCraft, for example, you could take a grandmaster and have it teach it 100 games, and then would it learn faster than taking someone who was like a beginner at StarCraft, or sort of a spectrum, so going from a beginner to an intermediate player to an expert in providing all of that data? Where do you think they would be able to learn faster? Would there be a difference or not?
Yeah, so we have looked at that a little bit, and your learning rate is definitely affected by the demonstrations, but it's not always as simple as you think, because this actually goes back to the curriculum learning. When you're starting off learning StarCraft, if you look at a grandmaster playing StarCraft, you're going to have no idea what they're doing. So you probably want to learn from someone who's not very good, and then shift. Another way you could think of that, instead of that sequential thing, is saying, I've got a bunch of demonstrations, which one should I pay attention to now? And try to figure out, okay, these are the ones I can handle. And now I can get some more complex ones. And then, and that comes more to the crowdsourcing thing, where you're trying to understand the different people giving you this information. What are their strengths and weaknesses? And that would be a great PhD or two worth of questions.
Do you find having a human guide the learning process? So it basically relates to what everybody has just talked about here, where it's better to have the system learn from, maybe from suboptimal behaviors that are easier to understand. You could imagine having a human who is overseeing the learning process and prompting the system to select actions which maybe are suboptimal in the global sense, but they help the system explore the state space and kind of learn the reward function and the Q values gradually and faster.
So I'm not sure anyone has looked at that. We've been talking about, because we've done some agents providing advice to other agents, or human providing advice. So trying to figure out where you could say, oh, you should go right, you should go up. But sometimes, like you were hinting at, it might be better to give bad advice. So if you're in a video game, maybe it makes sense to say, you jump off that cliff, so that you learn cliffs are bad and learn that right up front. And that might make sense for a video game, but it's not going to make sense for a robot. Because if you tell the robot, oh, look, if you do this thing, you will break this joint, you really don't want to demonstrate that. But that idea of humans guiding learning, I haven't really seen. I think I've seen some of that in planning, but that I'm not sure people have done it in reinforcement learning. That would be kind of cool.
Because in planning it's sort of interesting because, well, there's no learning. I mean, everything is sort of known.
All right, this is awesome. I love that you guys are asking questions and throwing out ideas. So that means I'm just going to say that in Mario, it works. Did my computer freeze? That's cool. So let's see. So here we've got the human demonstration in the flat red line. Our best method is, in this case, is dynamic IRL shaping. And we see the same thing that we did before, that if we look at basic RL, it's in red here, and it learns to outperform the human, and other ways of injecting human knowledge help. And it turns out our way of creating this potential-based reward helps you learn faster.
What are the ends?
Sorry, the what?
The numbers, like 20M, 13M.
Sorry. So this is the total reward. So if we look at the total reward accumulated, another way, so there's a bunch of ways of evaluating reinforcement learning. One of the standard methods is area under the curve. Another one is asymptotic performance, or final performance in a graph. And we've got some results about if you give more demonstrations, you are able to learn faster, like you would expect. So where does this leave us? One of the reasons I think people, at least one of the reasons I think it's interesting, is we're using inverse reinforcement learning in a place where we didn't have a model. And we could do that because there are a few IRL methods that don't require a model. So that way, we're able to do model-free learning and still look at a human's demonstration, figure out what was the human's reward, and try to leverage that. And it seems to work. We're able to increase the area under the curve. We're able to outperform the human. Great. Those were the things I wanted to do. Now, one of the drawbacks, of course, is I showed you that huge chart with all these different methods. It's not really clear when one method's going to work better than another. So these two methods I just talked about were the kind of the final two algorithms in Ben Sway's PhD thesis. If he was there for another year, I really would have liked him to try to tease out, if your demonstrator is like this, you want to use this method. Or if you only have so much demonstration, if you've got a lot of it, maybe you want to use this other method. We don't really have a good sense of that. We don't have a good way of trying to take multiple demonstrators yet and decide when to use them. That's something we should be able to do. We'd also like to think about, I've talked about a bunch of ways of leveraging human data. It would be nice if we could combine some of them. There should be some ways that, that some algorithms are good at this part, and other algorithms are good at this part of the learning. All right, so what I'm not going to talk about today is teaching agents to learn from human reinforcement. So we've got an agent in the world, and it's not an MDP because there's no reward signal coming in. And you think about this, I've got a robot at home, and I need to teach it to clean up my child's toys. I'm not going to come up with a reward function. But what I could do is train it like a dog, where I can say, that was good, that was bad. And we can use some kind of Bayesian framework to do this. And it works pretty well. So you can look at the history of states and actions, and the agent can learn to try to maximize your feedback. The main thing, the reason I do want to mention this is the one I think really cool thing is that there's also neutral. So when I say you give positive and negative feedback, turns out a lot of time, like when you're training your dog, you're not constantly saying good boy, good boy, good boy, good boy, right? You can give rewards, you can give punishments, or you can say nothing. So with my daughter, it turns out we primarily use positive reinforcement. We clap when she goes down the slide without falling head first, and when she falls, we don't berate her. We pick her up and stop her crying. Whereas undergraduates, it's all punishment. You just look at their test and say wrong, wrong, wrong. And so when I'm not saying anything to my daughter, she might interpret that as, oh, maybe I'm not doing the right thing. Or if I'm just not yelling at my students, they can assume they're doing the right thing. So different people mean different things by neutral. So we did a bunch of crowdsource experiments and found this was true. That we could identify on the fly using this Bayesian framework, we could figure out what no feedback meant for different people. So I'm going to skip this other stuff and get to, thank you, and say we also used a robot.
We will start with a high leveler, which allows us to give a +1, -1, or
so
+4
here we've got an example of a turtle bot and a Wii remote, where we can actually give good job, bad job.
A larger history of behaviors. The task is simple, and train the turtle right in
Here we
front
go.
of it and punish
So
it when
here
it
we're
does it wrong.
teaching kind of a lure behavior. So you're teaching the robot to follow this pointer.
And then adding a number of rewards when it does the correct behavior. Next, we give feedback to get the turtle.
And what we were doing is basically showing that we can use this not only in simulation, but on physical robots. Because the end goal of this is really to say we want reinforcement learning agents interacting with real people. If the task is not defined in the laboratory, a non-expert human generally can't define an MDP, but a human can say, hey, that was good, hey, that was bad. So we can show that we can learn fast. And since I'm an academic, we can show that we have to show that it works better than other people's. So we do that too. So we are able to learn policies for these agents. I didn't talk at all about, we're actually learning some language, natural language in here, and adaptive speed. So we've done a little work on saying when the agent is unsure, it should move slower. So that's a way of giving an implicit cue to the trainer. If you want to give me some feedback, now would be a great time. Where we're going with this, with something that we may have just submitted to AAAI as a paper, is on this curriculum design. So if we want our agent to learn this difficult task, how do we pick the sequence of tasks so that we can learn that task faster? And can non-expert humans do that? So that was a whirlwind tour, some of the things I'm not talking about today at all are learning from crowdsourcing, doing transfer learning, lifelong learning, multitask learning. We've been doing that in simulation and on robots. Oh yeah, and we do robots too. So we've been working with John on a semi-autonomous wheelchair. We're doing a bunch of agricultural work because Washington State, out in the middle of nowhere, we've got a good ag school. We've been playing with flying robots because flying robots are awesome. And we've been starting to actually look at this learning from demonstration with non-experts. And in particular, looking at them playing with UAVs or drones. So when you get someone in and you tell them this is an expensive drone versus this is a toy, how does that change how they demonstrate? All right, so where does that leave us? I spent most of our time talking about how we could take reinforcement learning and speed that up from human demonstrations. I very quickly mentioned some work that we've done where we can directly learn from human input. But those are both ways of humans interacting and helping agents or robots learn. And that's really where I think a lot of people in our field is going, saying that's great, the DeepMind stuff where you've got an agent able to play on a simulator is amazing. But there's lots of cases where you don't have the ability to train for months, or maybe because it's really expensive, or maybe there's not a well-defined goal and you need that human interaction to define the goal. I often talk about my work. Of course, this is not my work. This is actually the work of the students in bold. The other supervisors are not in bold, but this has been a ton of work by a lot of different people. It was funded mostly by the Air Force and NSF. And I think we have a few minutes if there are any remaining questions. Yeah, Andre.
Do your methods make any assumptions about the feature set that's used by the artificial intelligence system versus the feature sets used by the demonstrator?
No, I don't think. Do we make any assumptions? Well, so like when we were in the maze domain, the features are actually different because the agent just sees X and Y, whereas the human sees the entire maze. So, and in Mario, the human has access to the entire screen, whereas the agent is summarizing that screen in terms of 27 features. So they really do have different ways of describing the world.
Okay. I mean, it seems like in the toy domain that you demonstrated the maze, you say if you remove the X feature or the Y feature, right, suddenly the agent will not be able to learn anything. Right. So I guess maybe you have been getting, I don't want to say lucky, but somehow the feature set that you would be picking for the agent would happen to contain enough features for them to pick up the policy.
Well, and there's two things here. One is, does our state representation adequately describe the world so that I can learn to perform well? There's also, does the state representation let me represent the human's policy? So if I'm going around this maze and I can only go down when the red light is on, and the human and the agent can't see the red light, but the human can, then the agent is never going to understand the human's policy. And that would be a fatal flaw, I think.
But this has never happened in your experience.
Yeah, surprisingly, somehow we picked domains where that wasn't an issue.
Well, I guess since you as the human were also designing the feature set for the artificial intelligence agent, you were probably kind of designing it knowing what the features that are relevant.
Yeah. So in the case of Mario, and Keep Away, I can say we were using existing features and the human was using just the visualization. But you could definitely, I don't want to call it cheating, but if I was being careful, I should be able to design a state space so that I could represent the human's policy, no matter what task it was in. In this case, I can say, well, I was just using the existing state features, so I didn't have to tweak anything. So maybe I just picked good domains. Yeah?
So in the real world, if a human or a robot is observing a human demonstrating something, there's some recognition process that has to happen before he can interpret that as a real demonstration. Is there any work on just having the human point to certain areas that might be of sort of high value state or an area of attention that the agent should look at? Sort of the shortcuts to the demonstration.
Yeah. Believe Jeff Hollinger at Oregon State was doing something similar using like eye tracking. So thinking, let's say you're trying to balance a pole. Then if a human's balancing a pole, they're probably going to be looking up here at the top of the pole. They're not going to be looking, over to the side. So you could think of using the human's gaze to figure out what's important. Or you might think that a human could just, if your human's watching Mario play or a robot doing something and say, oh, that was a critical thing. So that, oh, well, once you made that mistake, it didn't matter what you did. And that would be a nice shorthand way of saying that's important. I don't think that's very well developed, though, and there should be people working in that area. Yeah.
This might seem like a somewhat odd question, but is there a way to train this or to train the model to mimic human mistakes? So you don't want the model in many situations to be too good. So video games, for example, right? If this was a way to train an AI in a video game, there are lots of studies that show people don't like it when the AI is way better than they are in video games. So would there be some way to compensate, perhaps, this example to controlled overfitting, where it would make the same mistakes a human would make?
Yeah, because you don't just want them to be suboptimal, but you want them to be suboptimal like a human.
Like a human, exactly.
Yeah, so haven't thought about this. One way to do it, so if you just try to mimic the human, you're going to get probably some weird behaviors because you don't have enough data to fully, perfectly perform as the human. But if you could come up with a reward function, and the reward function is not play perfectly, but maybe using inverse reinforcement learning to try to play as well as the demonstrated thing, so make the same number of mistakes, So I don't know that anyone has looked at that. That sounds like a really hard problem to come up with an optimization criteria. But if you could, it would be normal reinforcement learning. Neat problem.
So I was wondering if, imagine the setting where human is doing demonstrations, but the human doesn't precisely know the exact sequence of, so it's not about suboptimal action. Imagine the human is sort of, let's say the maze example, where you don't show the whole maze to the human. You still want the human to try and get to the destination. So the human, while doing the demonstration, is doing some mix of exploration and exploitation. Now it seems like that is a very different type of demonstration. Would that even fit into this formulation, this formalism of learning from demonstrations? Just curious.
You lost me somewhere. Can you say again how you were defining demonstration?
Demonstrating to the robot, if the human is doing some sort of exploration and exploitation, and the robot doesn't know what is exploration, what is exploitation, is that sort of demonstration, can it be somehow incorporated?
So I think a related question would be, what if your demonstrator is learning the domain as they're demonstrating?
Or if they didn't have this full state information, and so that's for the maze example, I can think of this situation where the human is not shown the whole maze, right? And you still ask them to get to the destination. They will be able to do it, right? It's just like the robot if they have a limited field of view. So in this situation, yes, you have this the demonstration is not optimal in that sense. So how would you? Is there a way to somehow handle that?
I'm sure there's a way. I just don't know it. Yeah. So what I would probably try to do is say that it's that the human's demonstrating a non-stationary policy, or the human's policy is non-stationary, and I would probably try to treat all these. Rather than saying this is a bunch of data, I'd probably try to treat these trajectories differently and have some way of figuring out, oh, the trajectories towards the end are actually much better. So if I'm training, I should either only look at these or weight these much higher, or weight them based on the reward performance or something. So that maybe there's something you can learn from these first demonstrations, even though they're not very good. But we typically assume, in all of our experiments, we assume that the human has some policy that they are demonstrating and that policy is fixed. You could also think that if the human is learning, maybe that process of learning could teach you something important. That you could see that the human was trying to do this thing and then stopped. And you could infer that, oh, that's a bad action. Not only is this other action good, but that's bad. I don't know anyone who's looked at that, but that's pretty cool. It could be a cool idea.
Just a comment on that. It seems like you might learn something new and valuable from that, in that you might learn the strategies humans learn in an unknown environment, and then you'd have a generalizable set of skills that might work better in other mazes.
Yeah.
Not quite.
So how do these systems, if you're trying to learn from a human, account for like the perseverance aspect? So since you gave the example of Mario, there's plenty of times where many people die trying to jump over arbitrary chasm, either because their timing is slightly off or whatever. So the human's going to keep trying, and there's lots of information there. Is the system just naturally going to pick up and say, oh, well, if they eventually get across, that's a good thing, or?
Hopefully.
Okay.
Even if it's really hard to do, hopefully if it sees a positive example, it'll understand that. The perseverance is also interesting because if you have a human that's trying to train an agent, at some point they might just say, forget it, I don't care anymore. And being able to identify that, or try to combat that by keeping the human engaged is something that you see a lot in crowdsourcing type things. Or so I've heard. Great. Well, thank you so much for coming, and I really appreciate the questions.